Introduction to Quantum Information Processing. We are now starting part 2 of the course, Introduction to Quantum Information Processing. The next several lectures will be on the subject of quantum algorithms. The first quantum algorithms that you'll see are simple ones that introduce some underlying ideas. Then we'll work our way towards increasingly sophisticated algorithms, including Shor's factoring algorithm and Grover's search algorithm. This is lecture 5, the first lecture in part 2 of the course. In this lecture, we're going to see a basic picture of classical and quantum algorithms as circuits. We'll consider simulations between classical and quantum circuits, and we'll see the Toffoli gate. We'll also have a quick look at some of the basic computational complexity classes associated with classical and quantum algorithms. Let's start with classical logic gates. Recall that the NOT gate takes one bit as input and outputs the logical negation of that bit. This is the notation for a NOT gate that's traditionally used in electrical engineering logic diagrams, and these are more modern ways of denoting the gate. The logical AND gate takes two input bits and produces one output bit, which is 1 if and only if both input bits are 1. This is electrical engineering notation for the AND gate, and this is more modern notation. The fan-out operation is often implicitly used in circuit diagrams. It's essentially a copying operation whose output bits are multiple copies of its input bit. Recall that it is possible to copy classical information. Fan-out of the output of a gate is denoted this way. What about the logical OR gate? We don't need it as one of our fundamental operations because it can be simulated by 3 NOT gates and 1 AND gate using the so-called De Morgan's law. The XOR gate, where XOR means exclusive OR, can also be simulated by AND and NOT gates. Every 3-bit string has either more zeros than ones or more ones than zeros. Define the majority of a 3-bit string as the most common value. Here's a classical circuit that computes this majority function. The input bits, A1, A2, and A3, are shown on the left. Information flows from left to right, and the output bit is B. The circuit is based on this formula in terms of AND and OR operations, where the OR gates are simulated by NOT and AND gates. The total number of gates is 9. Suppose that n is an odd number larger than 3. Can you construct a classical circuit for the majority of n bits for those values of n? What is the gate count of your construction? Does it grow polynomially or exponentially with respect to n? Can it be made to grow polynomially? We can represent algorithms as logic circuits along the lines of this diagram. The input bits are on the left, time flows left to right, and the outputs are on the right. Classical computer algorithms are usually described in high-level languages, but they implicitly describe sequences of low-level logic operations like this circuit. A reasonable overall cost measure is the number of gates. There are other measures that we may care about, such as the depth, which is the length of the longest path from an input to an output, and the width, which is the maximum number of gates on any level, assuming that the gates are arranged in levels. But to keep things simple, let's just use the gate count for now. The number of gates depend on what the elementary operations are. We'll take these to be and not gates. What's important is that an elementary operation does a constant amount of computational work. If we allowed arbitrary gates, then, well, any circuit could be reduced to just one supergate. But the cost of that one gate would not really be very meaningful, since we expect large gates to be expensive to implement. Okay, let's consider the multiplication problem, where one is given two n-bit binary integers as input, and the output is their product. For example, the product of 5 and 7 is 35. But think of the number of bits n as being quite large, larger than the number of bits of the arithmetic logic unit of your computer. Do you know of an algorithm for performing this? I believe that you do know of such an algorithm because you learned one in grade school. In principle, you could multiply two numbers consisting of thousands of digits by pencil and paper using that method. How efficient is that algorithm? If you learned the same algorithm that I did, then its running time scales quadratically in the input size. By quadratic, I mean some constant times n squared. The constant depends on the exact gate set that you use, and we'll often use the big O notation to suppress that. Of course, if we want to implement an algorithm, then we do care about how small that constant can be. But if we're looking at things theoretically, then the big O notation helps us focus attention on the underlying growth rate. There are more efficient algorithms than the grade school method. The current record is order n log n, which is quite good. There's actually a rich history of multiplication algorithms that evolved from n squared to n log n. By the way, that n log n algorithm is actually only a few years old. But we won't get into that history here. Now let's look at the factoring problem, which is sort of the inverse of the multiplication problem. The input is an n-bit number, and the correct output is the prime factors. For example, for 35, the output should be 5 and 7. You probably also learned an algorithm in grade school for factoring numbers. You check if the number is divisible by 2, then you check 3. You can skip 4 since it's a multiple of 2. You check 5. You can skip 6. You check 7, and so on. You can stop once you get to the square root of the number, because if you haven't found a divisor by then you know that the number is prime. How expensive is this computationally? For large n, there are lots of divisors to check, exponentially many. The cost is exponential in n. There are more sophisticated algorithms than that. The best currently known classical algorithm for factoring is the so-called number field sieve algorithm, which scales exponentially in the cube root of n. Since the cube root is in the exponent, this is still essentially exponential. There is no currently known classical algorithm for factoring whose cost scales polynomially with respect to n. In fact, the presumed difficulty of factoring is the basis of the security of many crypto systems. Now let's consider quantum circuits. The input data is on the left, as computational basis states. Data flows left to right through a series of unitary gates, and then measurement gates occur at the end, which yield the output of the computation. Again, we can take various cost measures of a quantum circuit, such as the gate count, the depth, and the width. Let's focus on the number of gates. Also, we need a notion of what an elementary gate is that does a constant amount of computational work. For now, let's take that to be the set of all 1-qubit and 2-qubit gates. We'll consider simpler gate sets later on. Here's the factoring problem again. Shor's famous factoring algorithm is a quantum circuit for factoring consisting of only order n squared log n gates, a polynomial number of gates. Of course, an efficient implementation of this algorithm would break several crypto systems. Okay, so we're thinking about classical and quantum computations as circuits. How do these two models compare? Two natural questions are, can quantum circuits simulate classical circuits? Although our poly X gate can be viewed as a NOT gate, what about AND gates? None of the unitary operations that we've seen so far resembles an AND gate. And what about the other way? Can classical circuits simulate quantum circuits? We're going to address these questions. First, I'd like to show you a 3-qubit gate called a Toffoli gate. It's denoted this way, sort of like a controlled NOT gate, but with an extra control qubit. On computational basis states of the form ket A, ket B, and ket C, it negates the third qubit if and only if both of the control qubits are in state ket 1. Otherwise, it does nothing. This implies that the unitary matrix for the gate is this. For arbitrary 3-qubit gates that are not necessarily computational basis states, the action of the gate is to multiply the state vector by this 8x8 matrix. The Toffoli gate is sometimes called a controlled NOT gate. This makes sense if we start with the controlled NOT, the C NOT gate, which is a 4x4 unitary matrix, and then construct a controlled version of that gate, the controlled C NOT gate. The Toffoli gate enables us to efficiently simulate classical circuits with quantum circuits. The result is that a classical circuit with n gates can be simulated by a quantum circuit with order n gates. We use Toffoli gates to simulate AND gates, like so. Bits are represented as computational basis states in the natural way. So ket A and ket B represent bits A and B. To compute the AND of A and B, a third ancilla qubit in state ket 0 is added, and then a Toffoli gate is applied. Notice that this causes the state of the ancilla qubit to become the ket of A and B. The first 2 qubits can be discarded or just ignored for the rest of the computation. So that's how an AND gate can be simulated. And as mentioned earlier, the poly X gate effectively performs the NOT operation. Remember that circuit for computing the majority of 3 bits that we saw earlier? Here's a quantum circuit that simulates it using Toffoli gates for AND and X gates for NOT. The output of the circuit is the last qubit. Some classical algorithms make use of random number generators, and we have not captured that in our definition of classical circuits. Say we allow our classical circuits to access random bits that are 0 with probability 1/2 and 1 with probability 1/2. Can we simulate such random bits with quantum circuits? You may pause the video to think about this. Okay, it's actually quite easy, since constructing a ket plus state and measuring it yields a random bit. But this entails an intermediate measurement, Our quantum circuits will not look like the ones that we defined earlier, where all the measurements are at the end. Can we simulate random bits without the intermediate measurements? The answer is yes, by the following construction. Instead of measuring the ket plus state, we apply a C0 gate to a target qubit, an ancilla, in state ket 0. Then we ignore that ancilla for the rest of the computation. The final probabilities when the circuit is measured at the end will be exactly the same if a random bit had been inserted at that place in the computation. I will leave this as an exercise for you to prove that this works. You may have noticed that we defined quantum circuits to be in terms of 1 qubit and 2 qubit gates, but our simulation of classical circuits by quantum circuits used 3 qubit gates, the Toffoli gate. We can remedy this by simulating each Toffoli gate by a series of 1 qubit and 2 qubit gates. I'm going to show how to do this. To start, we will make use of a 2 by 2 unitary matrix that has the property that if you square it, then you get the poly X matrix. Since the poly X is also a knot, this matrix is sometimes referred to as a square root of knot. Note that in classical information, there is no square root of the knot gate, so it's kind of a curiosity that this is possible in the context of quantum information. Okay, let's refer to this matrix as V. I'll leave it as an exercise for you to come up with a 2 by 2 unitary matrix V such that V squared is the poly X. Henceforth, I'm going to assume that we have such a matrix V in hand. From this, we can define a controlled V gate. Also, we can define a controlled V star gate. Now, look at the following circuit consisting of 2 qubit gates. I claim that it computes the Toffoli gate. How can we verify this? Let's look at 2 possible approaches. The first approach has the advantage that it's completely mechanical. No creative idea is needed to carry it out. What you can do is work out the 8 by 8 matrix corresponding to each gate, and then multiply the matrices and see if the product is the matrix for the Toffoli gate. A word of caution, gates go from left to right, but the corresponding matrix products go from right to left because we multiply vectors on the left by matrices. The second approach is to try to find shortcuts based on an understanding of the logic of the gates to avoid tedious calculations. In this case, note that it is sufficient to verify that the gates are equivalent when the first 2 qubits are in computational basis states ket 00, ket 01, ket 10, and ket 11. Consider the ket 00 case. In this case, none of the controlled qubits do anything, so the state doesn't change, which is consistent with what the Toffoli gate does in the ket 00 case. What about the ket 01 case? Then none of the gates controlled on the first qubit have any effect, so the circuit reduces to a controlled V followed by a controlled V star, which simplifies to identity. I'll leave it to you to analyze the ket 10 and ket 11 cases. This kind of approach, when it can be made to work, has 2 advantages. It avoids a tedious calculation. In addition, thinking about it this way, we can gain some intuition about why the circuit works. In the future, if you need to devise a quantum circuit for something on your own, then you may need to have some intuitive understanding as a guide. Let me end this topic with a more challenging question. Suppose that we want to simulate a Toffoli gate using only controlled NOT gates and 1-qubit gates. Thus, no controlled V gates are allowed. The C0 is the only 2-qubit gate allowed. Is there such a circuit that computes the Toffoli gate? The answer is yes, though the circuit is a little more complicated than the one above. I'll leave it to you to devise such a circuit. So we've seen that quantum circuits can simulate classical circuits. Can classical circuits simulate quantum circuits? The answer is yes, but the only constructions currently known have exponential overhead. A quantum circuit of size S, acting on n qubits, can be simulated by a classical circuit of size order S n squared 2 to the n. So the simulation is not efficient. It requires exponential classical computing resources. But at least it's within the realm of computable, that is, unlike the halting problem. And at least it's not double exponential, like 2 to the 2 to the n. So this bound is worth something. The idea of the simulation is quite simple. An n-qubit state is a 2 to the n dimensional vector. Store the components of the state vector in an array of length 2 to the n. For each entry of the array, we can store the amplitude with n bits precision. So our accuracy can be within 1 over 2 to the n, which is pretty good. The initial state is a computational basis state. Each gate corresponds to a 2 to the n by 2 to the n matrix, and the effect on the gate is multiplying the state vector by that matrix. In fact, that matrix will be sparse, with only a constant number of non-zero entries for each row and column. Therefore, there are a constant number of arithmetic operations per entry of the array. Let's allow order n squared operations for each arithmetic operation, using simple grade school algorithms for multiplication, for example. Then the cost is n squared times 2 to the n for each gate in the quantum circuit. We multiply that by the number of gates in the quantum circuit, which is S, to get order S n squared 2 to the n. That's how much it costs to get the final state just before the measurement. What about the measurements? For this, we compute the absolute values squared for each entry. Again, that's 2 to the n arithmetic operations. At this point, the entries of the array are the probabilities after the measurement. The output of the quantum circuit is not the probabilities. It's a sample according to the distribution. How do we generate that sample? First, we sample the first qubit of the output. The probability that this bit is 0 is the sum of the first half of the entries of the array. Once we have the first bit, we can use a similar approach for the second bit, using conditional probabilities conditioned on the value of the first bit, and so on for the other bits. This also costs order n squared 2 to the n. This completes the classical simulation of quantum circuits. Note that if we take the quantum circuit for factoring that results from Shor's algorithm, and then simulate that quantum circuit by a classical circuit, the result is not very efficient. It's exponential, and in fact it's worse than the best already known classical algorithm for factoring. The simulation algorithm that I've just described is exponential space in addition to exponential time, because it stores that large array. In fact, there is a way to reduce the space usage to polynomial, but without reducing the time, or the number of gates. That part still remains exponential. I'll leave it as a fairly challenging exercise to figure out how to reduce the space from exponential to polynomial. In theoretical computer science, there are various taxonomies of computational problems according to their computational difficulty. And I'll briefly show you a few of these and how the power of quantum computers fits in with this classification. Consider all binary functions over the set of all binary strings. So these are problems where the input is a binary string of some length n, but where n can be anything, and the output is 1 bit. These are sometimes called decision problems, since the answer is a binary decision, 0 or 1, yes or no, accept or reject. This is a common convention for reasons of simplicity. Most problems that are not naturally decision problems, like factoring, can be reworked to be expressed as decision problems. The complexity class P, standing for polynomial time, consists of all computational problems that are solvable in polynomial time, which translates into our circuit formalism as polynomial-sized circuits. By polynomial, I mean bounded by a polynomial of the input size n. The class BPP, standing for bounded error probabilistic polynomial time, is the analog of P for probabilistic algorithms. It's usually defined in terms of error probability being bounded by some constant below 1/2, such as 1/4. Now, error probability 1/4 doesn't sound so good, say, for a self-driving car or an aircraft stabilization system. But this can always be amplified by running the algorithm repeatedly and then taking the majority output value of the runs. This reduces error probability 1/4 to error probability exponentially small while maintaining polynomial time. The class BQP, standing for bounded error quantum polynomial time, is the analog for polynomial-size quantum circuits, again with error probability up to 1/4 allowed, and that can be amplified to exponentially small error by taking repeated runs. And the class exp, standing for exponential time, is for problems solvable by exponential-size classical circuits. We have the following known containments, where BQP relates to the power of quantum algorithms. This is the end of Lecture 5. In the next lecture, we'll see our first quantum algorithms, which are able to outperform classical algorithms in a certain sense.